All right, let's talk about Chapter 9. So, this will be your video lecture on Chapter 9, and it deals with the periodic trends. Now, the first thing that we talked about when we started this course was the periodic table of the elements, and the most important particle in chemistry is the electron. And the electron does all the chemistry that we're talking about. It does the metabolism. In organisms, it does all the inorganic chemistry that we've talked about. Electrons are lost, electrons are gained, electrons are shared. It's all about the electron. And periodic trends on the periodic table are all about the electrons, where they are, what their energy is, how they interact with each other, and how they interact with the nucleus. And you might remember from Chapter 8 that, and actually all through the course, that if we're talking about the vertical columns on the periodic table, if we go from lithium, sodium, potassium, rubidium, cesium on down the periodic table, that all those elements have similar properties. Why do they have similar properties? Well, from Chapter 8, that's because they all have the same valence shell electron configuration. They have the same number of electrons in their valence shell, and the electrons in that valence shell are arranged the same way. That's why elements in the same group, the same vertical column on the periodic table, they have similar properties. Okay, I know this wasn't going to go well. Similar properties, okay? And it's all due to the valence electrons. All right, and then as we go across the periodic table from left to right, you increase the number of protons in the nucleus and the number of electrons that are surrounding the nucleus, but that positive charge that's in the nucleus is attracting the electrons to it. And those electrons are at certain energy levels. And what this creates for us is a certain set of properties due to that positive negative charge, and we call it effective nuclear charge. So let me give you an analogy. Let's say you are sitting on a back porch with a naked light bulb hanging from the ceiling, and evening is coming on. You're sitting there, you're sipping on your mint julep, and in come all these bugs. Now, if you're a lucky bug, you wind up getting here first. And so you're getting the full effect of the light bulb, the heat, the radiant light, and you're a very happy bug if that's the case. But if you're late to the party and you can't kind of get in there, and I notice there is a small airplane flying around there too. If you're late to the party, you don't get the full effect of the light bulb because these bugs out here are kind of robbed from the heat and light of these inner bugs, which are shielding. And you might depict that looking like this. These bugs that are close to the nucleus, close to the light bulb, they are shielding the outer bugs, these bugs that are coming late to the party. And that shielding is what creates what we call effective nuclear charge in combination with the number of protons in the nucleus, the number of shielding bugs or shielding electrons that are preventing these outer bugs. And these outer bugs are the ones that are going to do the chemistry for us because they are the valence electrons in our little analogy, okay? So you have protons in the nucleus, and the more protons, the brighter the light, the greater the effective nuclear charge. The more shielding that you see, the lesser the effective nuclear charge because they're shielding these outer bugs or outer electrons from getting the full effect of the light bulb. Okay, I think that's as far as we can take this little analogy. Let's go to a better depiction of real atoms. Here you have protons in the nucleus, these red things in here, and you'll have any number of protons. If it's sodium, here's sodium, number 11 on the periodic table. That's why we say it has 11 protons. That's why its atomic number is 11, because you've got 11 protons in the nucleus. Now, you've got 10 of those electrons, 10 of those 11 electrons surrounding the nucleus. They're the core electrons. You've got the 2s2 and the 2p6 electrons. You got 1s2, 2s2, 2p6, and then you have this 3s1 electron, which is your valence electron in sodium, and it's not feeling the full positive charge of those 11 protons because of these shielding electrons. Just like in our bug and the light bulb analogy, they're preventing the valence electron from feeling the full effect of that 11 protons in the nucleus. Now, if we go over here to magnesium, magnesium also has 10 core electrons, but it's got one more proton in the nucleus. It's atomic number 12, but it's got the same 10 electrons. So the shielding is the same, but the number of protons in the nucleus is one greater than sodium has. So when we do the calculation, and you're not going to have to do the calculation, so don't worry about that. We're just going to talk about it qualitatively, but I will mention some numbers. So the effective nuclear charge, what this valence electron is feeling for sodium, is a mere plus 2.5, and then for the two valence electrons actually that magnesium has, because there's one more proton in the nucleus, same number of shielding electrons, it comes up to 3.15, a positive value. So there is greater shielding. So there's a greater attraction, not greater shielding, greater attraction by the 12 protons, which means that these electrons are a little harder to peel away from the nucleus than, let's say, sodium. Sodium's valence electron is really easy to peel away. Magnesium's a little bit harder, not that hard. Magnesium will give them up, but you only have the same number of shielding electrons. Okay, hopefully that's pretty clear. So we call this effective nuclear charge. The effective nuclear charge is a net positive charge that's attracting a particular electron, and generally what we're talking about is the valence electron. The outer shell electron is what we're talking about, because remember, it's those outer shell electrons that do all the chemistry. Z is the nuclear charge. That's the positive charge in the nucleus from the protons, the number of protons. S is the number of shielding electrons that are in the way. Those are the core, in our light bulb analogy, those are the bugs that got in the way. And so the outer shell electrons just don't feel the full positive charge. We call it the effective nuclear charge. And this is the equation that if we were going to do a calculation, that we would go ahead and apply. As I said, you're not going to have to calculate effective nuclear charge. We're just going to look at the periodic trends. So remember your subshells, the S, P, D, and F subshell. An S subshell can hold 2 electrons, a P subshell. There are 3 P orbitals. Each P orbital holds 2 electrons. Any orbital can hold a maximum of 2 electrons. Don't put any more in there. But there are 3 P orbitals, PX, PY, and PZ. Each one of those holds 2 electrons, so that's 6 electrons. And then the D subshell, there are 5 orbitals. Each of those will hold 2 electrons. That gives us 10 electrons in a D subshell. And then the F subshell can hold 14 electrons, because there are 7 F orbitals. Each one of those holds 2, so it's a maximum of 14 electrons in an F subshell. Now, generally speaking, the S subshell has greater shielding because the electrons are closer to the nucleus in a spherical orbital. The P subshell, which is dumbbell shaped, it is a little bit less shielding, but it still will be closer to the nucleus than a D subshell, which will be closer to the nucleus than an F subshell. The further away from the nucleus, the less shielding effect the electrons in those subshells that are further away from the nucleus, okay? Remember, 2, 6, 10, 14, S, P, D, F. That might be a question by itself on the next exam, exam 4. So here's our diagram. Here's the nucleus. Here are our shielding electrons, these guys down here. And remember, electrons have negative charge. And with those outer electrons, you have a negative, and you know negative and negative charges will repel each other. So you get a little bit of repulsion between the core electrons and the outer valence shell electrons, enhancing the shielding. So outer electrons are attracted toward the nucleus by the nuclear charge, but they're pushed away from the nucleus by repulsion of the inner electrons or core electrons. So calculating the effective nuclear charge, I'll run through this really quickly, but as I said, I'm not having you calculate nuclear charge. But here's how we would do it if we were going to do it. Core electrons shield a valence electron better than other valence electrons do. If electrons are in the same shell, they're not going to have a significant or they'll have a less significant effect than the core electrons that are closer to the nucleus. So Z effective, which just stands for effective nuclear charge, increases as you move left to the right across the periodic table. Why? More protons in the nucleus. If you go from sodium, 11 protons in the nucleus, to magnesium, you got 12 protons in the nucleus. And as you go from left to right, you keep adding protons in the nucleus, so effective nuclear charge increases. So this is one approach for estimating effective nuclear charge. Z, the number of protons, minus the number of core electrons. That is one approach. And then you could add some component of the valence electron. So it's about 85% or 0.85 times the number of core electrons plus the about 35% or 0.35 times the number of valence electrons. And that's how you would calculate this. But as I said, we're not going to do it. If you're at n equals 1, your electrons are as close to the nucleus as they're going to get. N equals 2, they're a little further away. N equals 3, further away. 4, 5, 6, and 7, they're further away from the nucleus. And if an electron is sitting here at n equals 7, it's not very attracted because all these electrons from n equals 1 through n equals 6 are shielding that valence electron from that positively charged nucleus. And yes, there would be a lot of protons in the nucleus, but they're not feeling a lot of love from the nucleus in the form of positive charge because all these electrons are in the way. They are shielding the outer shell electrons. So as you go down the periodic table, the atomic radius increases and the effective nuclear charge decreases. Now, I know the arrow here is pointed in the other direction because we tend to use the arrows to indicate an increase rather than a decrease. So as you go down the periodic table, the atomic radius increases, which means that the effective nuclear charge decreases because the electrons are getting further away from the nucleus. And so what we say is the effective nuclear charge increases going from bottom to top because the valence electrons are getting closer to that positively charged nucleus. All right, so go down the periodic table, atomic radius increases. Go from the bottom to the top, the effective nuclear charge increases because the electrons get closer to the nucleus. All right, as I go across the periodic table, as we said, you're at the same n principal quantum value. This is n equals 2, and this is n equals 2. So you're in the same electron shell, different subshell, but you're at the same electron shell. You're at the same general same general zone away from the nucleus. And as you go across the periodic table, the number of protons is increasing. So boron has 5 protons in the nucleus, and fluorine has 9 protons in the nucleus. So it stands to reason that fluorine would have a higher effective nuclear charge than boron because it has 9 positively charged protons in the nucleus, which are attracting the valence electrons to a greater degree. And all the other electrons are in the same valence shell as boron, carbon, nitrogen, oxygen, fluorine. They're all at n equals 2, and it's a p subshell. Okay, but we go down the periodic table in the same group, the same family. Just remember, as we're going down the periodic table, those electrons in the valence shell getting further away from the nucleus, the atoms are getting bigger, and so the outer electrons have less effective nuclear charge. They're further away from the nucleus, and they're more intervening, shielding electrons that are in the way. So atomic radius increases as you go down a group or a family. Same term, family, group, because the valence electrons are going into orbitals that are in higher energy levels. That just means they're further away from the nucleus. They're more easily removed, and it's just a higher energy. Just think of a ball that you pick up off the ground and you raise it over your head. That ball is at a higher energy level over your head than it was sitting on the ground. Sitting on the ground, it was closer to the ground and at a lower energy level. So the farther the electrons are from the nucleus, the higher the energy level. So 6s for cesium is bigger than 1s for hydrogen. That's in the same group 1 over there, that family of elements. It decreases, the atomic radius decreases as you go to the right across the period because the effective nuclear charge increases. Why? Because you've got more protons as you go from left to right. More protons, and the more protons, the stronger the attraction for electrons that are in that same shell, causing the outermost electrons to be pulled more strongly to the nucleus. That's why the radius decreases going from left to right. That's right. As you go from left to right, okay, the atoms get smaller. The radius decreases. The atoms, I'm sorry about that. The atoms get smaller as you go across the periodic table. More protons in the nucleus pulling the electrons closer to that nucleus. Over here on the left side, you have larger atoms, larger radius. You have less effective nuclear charge. And over here to the right, more effective nuclear charge because you have more protons in the nucleus. So this is a chart or a representation of actual atomic radii. They're measured in angstroms. And so atomic radii of the main group elements in picometers. And you know, picometers, 1 picometer is 10 to the minus 12th of a meter. So there are 10 to the 12th picometers in a meter. It's just a very small unit of length or radius because atoms are really tiny. Over here in this group, you have hydrogen. This is group 1. You have group 1. And as you go down the group from lithium all the way down here to cesium, you go from 32 picometers to 215 picometers. That tells you this radius is larger because the effective nuclear charge is less. As you go down the periodic table, those electrons that are in that valence shell are further away from the positively charged nucleus. even though you have more protons in the nucleus, they're shielded by all these intervening electrons that are mitigating the attraction of the bigger nucleus for the valence electrons. The radius gets bigger because the effective nuclear charge is decreasing, and so these outer shell electrons are more weakly held. Plus, you've got the in-principle quantum number. This is n equals 1, n equals 2, 3, 4, 5, and just think of it like we did before. Here's the positive nuclear charge. There's n equals 1, n equals 2, 3, 4, 5, etc., etc. The orbitals, the shells are getting further away from the nucleus. Okay? As we go from left to right, okay, what's happening? More protons in the nucleus. Okay, over here with neon, you've got 10 protons in the nucleus pulling on its 10 electrons. Over here, this is 9 protons in the nucleus, 8 protons for oxygen, and 7 and 6, and then 5, and all the way over here 4, and then 3 protons in the nucleus. As you get more protons in the nucleus, they're pulling, and they're all at n equals 2. And so they're pulling those n equals 2 electrons closer and closer and closer to the nucleus. So the atomic radius decreases from left to right. Okay. Ionic size summary. Okay, so here is an atom, and this is going to be typically a metal. And so let's think of this as sodium. Okay, so this is a sodium atom. It's got 11 protons. All right, so let's take a look at ionic size summary. It's going to be different for cations and anions. You remember cations are elements that have lost electrons, so they have a positive charge. They have more protons than they do electrons. Let's just go ahead and think of this as sodium. We use it a lot for this. This is sodium metal or sodium atom. Now, sodium has 1 valence electron, and let's say it gives up that electron in its valence shell, and that valence shell is a 3s shell, okay, or a 3s subshell. Now, if that electron leaves, you now have a sodium cation. That's an A right there. Sodium cation. It still has those 11, I don't know why I did that. It still has those 11 protons that are in the nucleus, but now it only has 10 electrons. So each electron is getting more of the nuclear charge because now it doesn't have to share with 11 electrons. It only has to share with 10 electrons. Not only that, once we get rid of that 3s electron, we're now down to n equals 2p. And it actually has the same electron configuration as neon. So we've lost an entire shell. So think of it like this. Here is the nucleus, and just pretend that that represents 11 protons in the nucleus. You've got the 1s, you've got the 2s, you've got the 2p, and then you have that 3s valence electrons, but it's going to leave. And when that 3s electrons, you drop down from 3s to 2p. And so this 3s electron is out of there. It's gone. The 3s subshell is still there, but there's nothing in it. And so the measured value for the sodium cation is smaller. If I were to do a visual representation of this, I would say the atom is bigger, and then you would just look at sodium. I would do it like this. So atoms are bigger than their cations, okay? Because you've lost a valence shell, okay? You've lost an entire electron shell here, and the outer shell electrons are getting pulled more tightly. Now, if we go the other way and we look at an atom, here is an electron in the valence shell of some atom, and let's say this atom, let's say it's something like chlorine, okay, might as well. So this starts out as an atom of chlorine, and it is a chlorine atom. But we're going to add an electron to this valence shell. So in comes another electron. It winds up in that valence shell. Now you have a little bit of electron-electron repulsion here, and also you've got 17 protons down here pulling on, and now they have 18 electrons. So there are now 18 electrons, and those 17 protons are having to pull on 18 electrons instead of just 17 electrons. And so if I were to visually represent that, I would say that the anion is bigger. Oh, that's hard to do. The anion is bigger. It's negatively charged. You know that's an anion. And it's bigger than the atom. So anions are bigger than their atoms. Cations are smaller than their atoms. And visually, this is how I might present it to you on a test, just using, let's say, some artwork better than this of balls. Anions are bigger than their atoms, and cations are smaller than their atoms. Okay, so I just realized that there's an animation here, so let's go ahead and use the animation. Here's our atom. It's going to give up an electron to become a cation. You have greater effective nuclear charge on the remaining electrons. You've also lost an entire valence shell in the case of sodium. And so your radius of the cation is smaller due to the loss of that shell and the greater effective nuclear charge on the remaining electrons. If I'm looking at, let's say, the anion, you add an electron, which creates a weaker effective nuclear charge on the added electrons because the positive charge has to be shared with another electron. So now you have 10 electrons. If we were talking about fluorine, it's got 9 protons in the nucleus. I used chlorine in the previous example. The main thing to remember here is that atoms are larger than their cations. The other way to say it is cations are smaller than their atoms. And then if we look down here at anions, atoms are smaller than their anions, or you could say anions are larger than their atoms. Remember the relationship between atoms and their anions, or atoms and their cations. And metals tend to form cations. They tend to give up electrons. That's just a property of metals. And then non-metals tend to gain electrons. That's a property of non-metals. Okay, these are actual relative sizes of ions and atoms. You can see here what we've got is lithium. Lithium is a metal. Lithium loves to give up its valence electron here. And so this is representing the cation down here. You can see that the cation is smaller than its atom. The difference is 130 picometers versus 76 picometers. That's pretty dramatic. You can go on down here to rubidium, where the atom is at 215 picometers, and the cation, after losing the electron, the atom, the cation is 152 picometers. Let's go over here to the anion group. These are the nonmetals. Here we have oxygen, and oxygen as an atom is at 64 picometers, and then once it gains its 2 electrons, it balloons up to 140 picometers. And that's the trend, guys. Now, just as you go down the periodic table, it's the same trend as for elements as it is for atoms. Everything tends to get bigger from top to bottom, and everything tends to get smaller going from left to right. Top to bottom, bigger, left to right, smaller. Okay, all right. Okay, let's take a look at the energy required to remove an electron from a neutral atom. Now, one thing, we call this ionization energy, and it is specifically the amount of energy required to remove one electron from an atom. So this is the equation for ionization energy. You have an atom or an ion over here on the left side, on the reactant side. You're going to hit it with some energy, enough energy. Remember the photoelectric effect, okay, that Einstein wrote a paper on and was awarded the Nobel Prize for. You bombard the atom, and if it's of sufficient energy, you can cause an electron to be removed from the surface of that particular element. And so what you wind up with is a cation, something with a positive charge, and an electron. So one way to remember this, if it's an ionization energy, the delta H is ionization energy. The amount of, it's endothermic because we're hitting the element with energy and it's kicking off an electron. So an electron winds up on the product side of this equation, and you've got a positive charge here. I'm going to actually show you a couple of other. We would call this the first ionization energy. And the reason we call it the first ionization energy is because you're removing an electron from an atom. If we wanted the second ionization energy, we would start with an ion. Now, you might imagine, since you've got the same number of protons in the nucleus for the cation of this particular element, that it would take some. So it's going to take more energy to remove the second electron. That would give you an element with a +2 charge, and again, you'd have one electron over here. So we would call this the second ionization energy. And if we were to start and do the third ionization energy, we would start with a 2+ over here. You'd have to hit it with even more energy to knock another electron off, which would give us a +3 cation plus one more electron. So this would be the equation for the first ionization energy. Then you would have an element with a +1 charge, hit it with some more energy. That would give you an element with a +2 charge and an electron over here on the product side. The third ionization energy, you would start with a cation that had a +2 charge, hit it with even more energy, remove a third electron off, which would give you a cation with a +3 charge and an electron on the product side. So ionization energy increases as you move to the right across the period. Why? Because of effective nuclear charge that increases as you move from left to right. Ionization energy decreases as you go down a group. Why? Because the electron you're going to remove is further away from the nucleus. The effective nuclear charge decreases as you go down a group. Now, we're going to take a look at some real data here. And I've got a little animation for you. And so you've got ionization energy on the y-axis. And here's our orbital diagram. And so let's start with hydrogen. Now, hydrogen has one valence electron, but it's very close to the nucleus. So here's hydrogen right here. Okay, it's got somewhere in the neighborhood of about an ionization energy of maybe 1,300, 1,400 kilojoules per mole of hydrogen. And that's the amount of energy required to remove one electron, which is fairly close to the nucleus, but there's only one proton in the nucleus. So let's zip up to helium. Now you'll notice that helium has the highest ionization energy of any element on the periodic table. How come? Well, because it has this very stable electron configuration. It has a filled shell, and because it has a filled shell, it's very stable. So filled shell, as you remember from chapter 8, filled shells, filled subshells, they're very, very stable. I know that's hard to read. Filled shell. So this is stable. And anything that's stable is low in energy. And so it's going to take a lot of energy to remove the electrons from that filled shell. And those electrons are really close to the nucleus. All right, so that's helium. Now we're going to drop down to lithium. Well, why does lithium have such a low ionization energy? Remember the electron configuration for the valence shell of lithium. It's only got one electron in that valence shell. It's a little further away from the nucleus than this is the 1s, this is the 2s, with this 2s1 electron. And so it doesn't take a lot of energy to remove that electron from the valence shell. Let's go ahead, jump up to beryllium. And for beryllium, it's a little bit different because, so this is beryllium, and beryllium has a filled subshell, a 2s subshell that is filled. This is also relatively stable, and so it's a little harder to remove that electron from this filled subshell, this 2s subshell. Now what's happening? Well, we're going to go ahead and let me go ahead and erase that. We're going to jump up to boron, which is atomic number 5. I did all my graduate work in boron chemistry. And boron has a little bit lower ionization energy because this electron is at a slightly higher energy level. Remember, 2s and 2p, the 2p is at a slightly higher energy level because of electron-electron repulsion. And so it's a little easier to remove the valence electron from that 2p subshell because of its electron configuration. And then we jump around from boron to carbon, and carbon has a slightly higher, it's got 6 protons in the nucleus pulling on its 2p electrons, a little bit harder, and then we reach another level of stability, which is nitrogen. So here's nitrogen, which is indicated up here, and you've got a half-filled shell for nitrogen. And half-filled shells, you know, are stable. So here we are half filled. So half filled, and you know half filled shells are stable. And so because it's stable, that says stable, trust me, it's a little harder to remove a single electron from this stable half filled shell. All right. We go on and we go on. Here we are. We're now at oxygen. Oxygen dips down a little bit because these two electrons have been forced to pair up. It's a little easier to remove an electron from oxygen than it is fluorine. Here's fluorine. Oops. Here's fluorine. And then finally, we get to neon, another noble gas. Now, I've gone ahead and done the electron configuration for neon in a couple of places here. Here it is. 1s2, 2s2, 2p6. We learned how to do that in quantum mechanics. 1s2, 2s2, 2p6. This is a filled shell, and filled shells are very, very stable. Okay? Filled shells are more stable than even half-filled shell. So notice all the trends here. All the noble gases have filled electron shells. They all have very high ionization energies. Now, they get lower as you go down the periodic table because they're following the same trend as every other element on the periodic table. The valence shell gets further away from the nucleus, so the amount of energy required to remove electrons from the valence shell as you go down the periodic table gets lower. So following the trends, and that's all I'm asking you to know are the trends. All right, and we've got different electron configurations here. Here's argon. Argon's electron configuration: 1s2, 2s2, 2p6, 3s2. That is your noble gas electron configuration. Very, very stable, filled shell. And this explains, using quantum mechanics, why the noble gases are so unreactive, because they're so stable. Okay? And there we go. There's so I wanted to go back just a moment and remind you that this peak right here, right there, represents nitrogen. And this is experimental data. And the reason that the ionization energy jumps up for nitrogen is because it has a half-filled shell. So we might call that an exception, because it's violating the trend a little bit, and that's because of its electron configuration and the half-filled shell. Now, so why the dip for oxygen? You can see there are other dips on this experimental data, but why the dip for oxygen? Well, that's because oxygen, which is sitting here, if the reason that it takes less energy to remove an electron from oxygen than it does nitrogen is because when you do that, what you wind up getting is you get a half-filled shell. So that's why the dip for oxygen. Okay, oxygen, which has this electron configuration, if you remove this electron, you get a half-filled shell, which is more stable. So it's a little bit easier to move this electron from oxygen's valence shell than it is from nitrogen, in which you had a half-filled shell. When you have oxygen, you remove that electron, you go back to a half-filled shell. So it's a little easier to remove that electron. Okay, let's move on. All right, and this is just telling you about what we just talked about, exceptions to the first ionization energy trends. That's those rise in energy, as in the case of nitrogen, you have to break up a half-filled shell, costs extra energy, and with oxygen, when you ionize, you get a half-filled shell, which costs less energy because a half-filled shell is more stable. Successive ionization energies for some main group elements. This is group 1 and 2, 5, 6, 7, and 8. Just taking a look. This is the amount of energy required to remove an electron from sodium. You can see that it's very low. The reason that it's very low is because sodium has that 3s1 electron. It really would like to get rid of it. That's why sodium doesn't exist as a metal on the planet. It exists as in its oxidized state as a +1 because it has such low ionization energy. Then as you go across the periodic table, you can see that the ionization energy has this tendency to increase. Now, here's something I want you to notice. When I'm looking at this chart, this is the first ionization energy, the amount of energy required to remove the first electron from an atom. This would be the second ionization energy, the amount of energy to remove the second electron, the third ionization energy, the amount of energy to remove a third electron, and the fourth electron, and so on, okay, down to fifth, sixth, seventh. And I want you to notice something. As we go across the periodic table, the effective nuclear charge increases. So now magnesium is going to be a little bit higher ionization energy, first ionization energy than aluminum. And the reason is that magnesium has the 3s filled subshell. And so that makes it more stable. Whereas aluminum has an electron that's sitting up here at a higher energy level, 3p subshell, and there's only one electron all by itself. And if it can get rid of that electron, then it has magnesium's very stable electron. So getting rid of the first electron in aluminum's electron configuration is pretty easy. That's why the ionization energy drops down. Now, as you remove the second electron from aluminum, it jumps up much higher because remember, if you remove the first electron, let's go ahead and just remove that electron. Now what do you have? You have magnesium's electron configuration, and that's a filled shell. This is pretty darn stable. So it takes a lot of energy to break up that pair. But let's go ahead and let's remove one more electron from aluminum. And when we do that, now it's got that one electron left. And so to remove that, remember, you got 13 protons in the nucleus with aluminum. And so when we remove the third electron, it takes even more energy. And when it does that, we wind up with the electron configuration for neon. Now, you know that aluminum is one of those always the same charge, 3 plus, and the reason for that is when aluminum loses 3 electrons, it has the same electron configuration as a noble gas, neon. That's neon's electron configuration. And so if I were to try and remove one more electron to make aluminum +4, how much energy would it take? It would take me 11,575 kilojoules per mole of aluminum. That would be a huge amount of energy. Look at the massive jump in energy required to remove an additional electron from aluminum. That's because aluminum 3 plus has neon's electron configuration, which is incredibly stable. So you might look for that kind of a jump on a test question where you see that you have a relatively low ionization energy, then a higher ionization energy, even higher, but not that much higher. And then you get this huge jump in ionization energy. And the reason for that huge jump is because you have a very, very stable electron configuration in a cation like aluminum. Let's look at some others. So here is silicon. Now, silicon, the first electron, pretty easy to remove. The second electron, not that hard to remove. It's getting harder because you've got 14 protons in the nucleus, and it's pulling on the successive electrons a little bit stronger. And then you remove 4 electrons. This is the 4th ionization energy. But once you've done that, now you're back to neon's electron configuration, and the amount of energy required to remove an electron from an electron configuration as stable as neon's, the filled shell, is just too hard. And so you get this huge jump in ionization energy. So you're going to want to look for that on a test. You're going to want to look for this big jump, and does that big jump happen at the second ionization energy, the third ionization energy, the 4th ionization energy, or the 5th ionization energy? And that'll tell you what element it is. So if we remove the first electron from sodium, pretty easy, 496 kilojoules per mole. The second electron is trying to remove the electron from neon's electron configuration, and then it successively, it increases going down the periodic table, but going to 4th, 5th, 6th, 7th, but not that much. Here's magnesium. It's got 2 electrons in its valence shell. So the second ionization energy is higher than the first ionization energy, but look what it does for the third ionization energy. It jumps up to 7,733 kilojoules per mole. That's because you've got noble gas electron configuration here. And you can see the trend. It gets, anytime you're trying to remove an electron from noble gas electron configuration, it's a big jump here. Same thing here. For phosphorus, you're going from 6,200 to 22,000. Again, that's neon's electron configuration you're trying to remove an electron for. And the reason that these numbers are getting bigger is because you have more protons in the nucleus, which pull more strongly on the remaining electrons. All right, hopefully that was clear. Please come to office hours and get clarity if you need it. So just one more time to remind you, each time you remove that electron that takes you to a noble gas electron configuration, every single time the ionization energy, the amount of energy required to remove the next electron, is huge, because you're trying to remove an electron from an electron configuration of a noble gas, in this case, neon. Okay. General trends in subsequent ionization energies. Ionization energy, the second ionization energy is greater than the first, because you've got the same number of protons and you're having to remove another negative charge from, let's say, a cation, then a neutral atom. Ionization energy 2 for sodium is much greater than that of ionization energy 1, because sodium cation has neon's very stable electron configuration, just what we've been talking about. Forming sodium plus 2 disrupts that stable electron configuration. For magnesium, it occurs in ionization energy 3, is much, much greater than ionization energy 2. Magnesium 2 plus has neon's electron configuration, just as we've been talking about. And so forming magnesium 3 plus disrupts that very stable electron configuration. So identify the set with the correct ranking of the first ionization energy. So this is the kind of problem that you'll see on the exam. And all you have to remember with respect to ionization energy is that high ionization energy is over here. So high ionization energy and low ionization energy. And as I said, we're just going to use our trends. So in general, ionization energy runs like that. This is higher and this is lower ionization energy. This is higher ionization, I'm sorry, this is lower ionization energy, this is higher. So low to high, when we're talking about the vertical column, this is low, this is higher, and then this is low with respect left to right. It increases from left to right. So if I'm looking at, let's say, aluminum, which is here, that's going to be relatively low compared to phosphorus, which is here, which is relatively low when compared to fluorine here. So the ionization energy trend is decreasing in that direction. So fluorine will have the highest ionization energy, and then phosphorus will have the next highest, and then finally aluminum will have the lowest in this particular group. And we could look at any other series of elements here. So let's just look at three other elements. Let's say we're looking at argon, sulfur, and germanium down here. And we're just going to use the trends. The higher ionization energy would be argon. It's a noble gas. And then we would go across to sulfur, which would have a higher ionization energy than germanium. We're just using our trends, guys. Okay? High ionization energy up in the corner, right-hand corner, and then low ionization energy down here in the lower left corner. Okay? Electron affinity is a little bit tougher. Here's the experiment. In the electron affinity experiment, what you do is you take a neutral gaseous atom and then you add an electron. Now, in order to add an electron, there actually has to be a place for the electron. So let's take a look at hydrogens. 1s, it's got one electron in its valence shell. There has to be an available orbital to add the electron. And so if we take an electron and we add it, we can add it. It completes this particular subshell. And so we'll get a release of energy. Energy is released, which is why it's on the product side. And remember, when energy, or delta H, and it should not be IE, it should be EA for electron affinity. That's incorrect. Okay. If we're releasing energy, and let's just think of heat, okay, or it could be light in the form of a photon, if we're, which it probably is, if we're releasing energy, we get, for our delta H, we get a negative value. So the larger the negative value, larger negative, the higher the electron affinity, okay, EA. And when we say higher electron affinity, more energy is released, that's indicative of this atom wanting this electron. So increased electron affinity gives you a more negative number. It means that the electron, as you move right across a period, and as you move up, you get an increase in electron affinity. That atom wants that electron more. Let's see what the next slide has to say. So electron affinity, the EA of an element is the energy change when an electron is added to a gaseous atom to form a gaseous anion. You need to remember that this is the way the equation is represented. You have an atom or a cation here, could even be an anion, but the electron is on the reactant side in this equation, and then you get a negative charge because you're adding negative charge to an element, okay? Or you get one more negative charge if you're adding it to something other than an element, okay, like an anion. So atom plus electron gives you negative charge, and you get a release of energy. Remember, negative delta H means exothermic. That means that energy is a product. Okay, you get an energetic product. Okay. Negative electron affinities represent a decrease in energy when the electron is added to a gas phase atom. It is exothermic, energy is released. Positive electron affinities reflect an endothermic process. You have to actually add energy to get an electron to be added to certain atoms. And we'll look at the electron configuration to figure out why that's the case. Okay, this is a table of electron affinities. Notice that you have mostly negative electron affinities for these elements. Why? Because if you add an electron, energy is released. Now you have some elements that are electropositive, meaning they don't want to accept the extra electron. In order to get them to accept the extra electron, you have to actually add energy, and that's due to their particular electron configurations. Most notably, look over here at nitrogen, which has an electron affinity greater than or equal to 0. You might remember that the reason for that is that for nitrogen, you've got this 2p subshell, and it is what? It is half filled. Because it's half filled, adding one electron to nitrogen gives you a less stable, a very much less stable electron configuration, and so nitrogen doesn't want to accept one electron. It will, on the other hand, accept 3 to become a nitride, a nitrogen with a -3 charge. But that would be because, why does it do that? Because that gives it neon's electron configuration. Now, let's go ahead and let's look at neon, and this is going to be true for any noble gas. If you've got a filled if you've got a filled shell or a filled subshell, as you do with helium, neon, argon, krypton, xenon, and even radon down here, these guys do not have a negative electron affinity, meaning that they don't want to accept electrons. Why? Because they all have filled shells. Okay, they all have filled shells. And so they're all electropositive. And we just explained why nitrogen, with its half-filled shell, has a greater than 0 electron affinity. Now, you'll notice a little bit of a violation of the trend. The electron affinities tend to be higher going from bottom to top, and that's simply because you have a higher effective nuclear charge going from bottom to top. The electrons are closer to the nucleus, and that closeness to the nucleus gives you an increasing effective nuclear charge. However, electron configurations matter, and size matters. So what we want to do now is we want to look at a little violation of the trend. No. Now, you might notice that the trend is violated a little bit with some elements. Ordinarily, as you go the down the periodic table, the electron affinity gets lower. It's a smaller negative number than the immediate element above it. But there are some violations of that. And so what I'm going to do is I'm going to take a look at that with respect to oxygen. So here is oxygen's valence shell electron configuration. It's exactly the same as sulfur's valence shell electron configuration, except that sulfur is one period lower than oxygen is. So sulfur is a little bit bigger. So sulfur is bigger, oxygen is a little bit smaller. And you'll notice that oxygen has a smaller electron affinity than sulfur does. Here's the general explanation. They're both more than willing to accept an extra electron. You have two orbitals that have, for each of them, that have unpaired electrons in them. You can go ahead and pair them up. You can add an extra electron in there. So they both have negative values for their electron affinity, but sulfur's is a little bit larger. And so generally speaking, I use this example. Think of a wedding reception. I went to one recently, and very often at a big wedding reception, you'll have round tables. And somebody always brings an uninvited guest. Well, if the round table is really small, it's going to be tough to fit that uninvited guest around that table. So one extra electron or one extra guest really makes a small table very crowded. Everybody has to elbow each other a little bit more, and we might call that repulsion. Okay, so repulse. Okay, sulfur is just bigger. And sulfur, because it's bigger, you can go ahead. So this was oxygen. We'll stick an electron in there. You have some electron repulsion. There's definitely room at the table, but for sulfur, it's a bigger table. So you have an easier time squeezing in that extra electron. And because it's a little bit easier, it's a little bit more stable. And so you have a bigger release of energy. And then the trend as you go down the periodic table, it starts to get restored. And eventually you wind up, like every other group, you wind up with lower electron affinities down below. But all these elements have the same electron configuration in their valence shell, so they violate that trend. Same thing over here with fluorine and chlorine. So fluorine, definitely big ion electron affinity at minus 328.2. Chlorine, a little bit bigger. Same explanation. Chlorine is a little larger as an atom than fluorine is, so it's a little easier to squeeze that extra electron. And then the electron affinity tends to go back down because the orbitals are getting further away from the nucleus. All right, so I promise that I won't give you anything that's too challenging on electron affinity. I would definitely remember that the equation for electron affinity is like this. Okay, you're adding an electron. That means it's on the reactant side, and you're releasing energy, which is why for electron affinity, you get a negative value for the electron affinities, and I'll just equate it to delta H. It's exothermic. This is an exothermic process, okay? And it's a measurement of how easily electrons are added to elements. I will give you a general trend. First of all, noble gases, they don't want the electron. They don't want to react at all. Non-metals definitely have higher electron affinities than metals. Look at metals. Metals have really low electron affinities. which tells you that metals are better at giving up electrons than they are accepting electrons. Okay? All right. These are just real values for the electron affinities. I'm not going to spend really any time on it, but these are measured values. You do an experiment with electron affinity. You take something like a neutral gaseous atom, you add an electron, you fire electrons at it with an electron gun, forms a negative charge over here, and it releases energy. Okay, so you get negative delta H over here, exothermic. All right, I think we beat that to death. Let's look at some electron configurations with respect to electron affinity. This is an old slide, but here we go. So we're going to do the same thing with electron affinity that we did with ionization energy. We'll just look at the electron configurations and compare them to the numbers. So first of all, here's hydrogen with a minus 73. It's got room in its valence shell, so we can definitely add an electron. That valence shell, it's 1s. It's really close to the nucleus, so we can pop in another electron. It releases a fair amount of energy for hydrogen. And then we'll go across. Now we've got helium's electron affinity. You've got a filled 1s subshell. If you're going to put an extra electron into helium, you have to put it in an entirely new electron shell, the 2s electron shell, which it doesn't want to do, and you can see that because it's got an electron affinity that's greater than 0, just like all the noble gases. And so let's move on. Here's lithium. Lithium definitely has room for the extra electron. There's not a big advantage to a lithium accepting the electron, but if it does, what it's got a filled subshell, a filled 2s subshell, and so lithium will definitely accept the electron, release a little bit of energy. But now, what have we got? Now we've got beryllium's electron configuration, and beryllium has that filled 2s subshell. It doesn't want to accept the extra electron because if it does, it has to put it way up here in the 2p subshell, and that's a big disadvantage energetically for beryllium, and so beryllium has greater than 0 electron affinity, which means it really just doesn't, you have to add energy. It's endothermic if you're going to get beryllium to accept this extra electron. Then we go over here to boron. This is boron's electron configuration, and no big deal. Boron can add the electron. It'll go into an adjacent electron or orbital that's at the same energy level. It'll release a bit of energy. Why does carbon jump up so much? Because if it accepts the extra electron, it winds up with a half-filled shell. Now, this is nitrogen's electron configuration, which is a half-filled shell. If it accepts the extra electron, it disturbs that stable electron configuration, so it really doesn't want to do it. Here's oxygen. It's perfectly capable of accepting the extra electron. And then here's fluorine. What's the big advantage for fluorine? It accepts the electron. It gives neon's electron configuration. So that's why you get this big jump between oxygen and fluorine. Fluorine has a high effective nuclear charge. It has a high electron affinity, not as high as chlorine because chlorine's bigger. Remember that. Same thing for oxygen. Sulfur is a little bit bigger, a little bit easier to add. Okay, I think that we've kind of beat that one up. There we go. Okay, general trends in electron affinity. Most elements have a negative electron affinity values, even metals. Elements with positive electron affinity values have filled energy levels like noble gases or sublevels of group 12. The periodic trend for electron affinity values of main group elements is to become more negative from left to right. until reaching the noble gases. Okay? And we've talked about the exceptions. All right, let's read the question. Identify the set with the correct ranking of electron affinity from most positive to most negative. Well, it seems to be, since most electron affinities are negative, you could say the least negative to the most negative, all right, rather than most positive. But the least negative is the most positive. So least negative equals the most positive. So if I'm looking at the trend, and if, let's say, I've got phosphorus and I've got aluminum and I've got fluorine over here, here's fluorine, definitely more negative than phosphorus. And then I suspect that aluminum, because remember the trend, it's like the trend in ionization energy, but there are some anomalies because of the electron configurations, the difference. But in general, the trend is like this, and this would be most negative, most exothermic. That's excluding the noble gases, because remember, they're all electropositive. And so this would be the least negative, that's aluminum, which is the most positive in this group. Most positive is the least negative. So I'd say aluminum is less, okay, in the way. So I'm looking for the most negative. So most negative is going to be fluorine. Phosphorus is less negative than fluorine is, and aluminum is less negative than phosphorus is. And we can check that out. Let's go back. There were a few slides back. We actually had values. Here you can see fluorine. Fluorine is a minus 238 kilojoules per mole. Phosphorus at a minus 72 kilojoules per mole. And then aluminum way down here at minus 43. So this is the least negative or most positive aluminum. And then the most negative is fluorine at minus 328. So we guessed right. Okay. And we're just using trends. I'm not really expecting you to know the numbers themselves. Let's take a look at electronegativity. Electronegativity is on a scale. It's called the Pauling scale and Pauli scale. And it's actually named for Linus Pauling scale. Linus Pauling, who is a famous biochemist who discovered the alpha helix secondary protein structure, awarded the Nobel Prize for that. And a very interesting guy, but at any rate, he combined using at the effective nuclear charge, he combined ionization energy, electron affinity, and came up with this scale for electronegativity. And you might just think of it as merely a measure of how strongly atom draws electrons toward itself in a covalent bond. The higher the electronegativity of an element, the more likely it attracts shared electrons. And on the Pauling scale, fluorine is the queen at an electronegativity of 4. And the general trend from left to right is an increase in electronegativity. And as you go down, you might suspect the periodic table, you have a decrease from top to bottom. Now, the noble gases are excluded from this because they don't want electrons. They don't want to do anything. They don't want to give them up. They do have a high ionization energy, but they have greater than 0 endothermic electron affinity, and their electron affinity is effectively 0. They just don't want to accept the electrons. So this is the general trend from left to right. Increase electron affinity to a maximum of 4. with fluorine, and then it decreases going down because the valence electrons are getting further from the nucleus in any available space to attract the electrons. Is further away from the nucleus. You have more shielding electrons. In general, the effective nuclear charge is decreasing, and so the electronegativity decreases. Okay, so it follows the rest of the trends in effective nuclear charge. Okay, so I generally look at it, go from fluorine, and just you can do the trend down here. Cesium at 0.7, fluorine at 0.4, and looking at hydrogen 2.1, helium is greater than 0, so it doesn't want the electrons. Lithium at 1, and as you go across, you have this steady increase all the way to fluorine. So this is low electron affinity and high, sorry, not electron affinity, electronegativity, high electronegativity. Fluorine's the queen, everybody else is less. So if I'm looking at a trend and I want to do what we did before, aluminum, phosphorus, and fluorine, you can see aluminum has a lower electronegativity than phosphorus does, which has a lower electron affinity than fluorine does, and I don't know why. I keep getting that. All right, we're almost there. Lattice energy. This is pretty much the last thing we're going to do in this chapter. Here's the experiment. You take ions, cations and anions. So here's sodium chloride. You have them in a gaseous state far apart from each other. Now, making bonds releases energy because it makes everything that makes the bond more stable. You're getting the positive and negative charges closer together. That releases energy. So when you coalesce these gaseous atoms, you release energy in the form of heat. So if I take sodium cations, chloride anions, and I combine them to make solid sodium chloride, you're going to get a release in energy. You get this negative delta H, and we call that the lattice energy. It's an expression that is a measurement of how strongly attracted to each other the cation and the anion are. Now, you might imagine if they're really strongly attracted, it would take a lot of energy to break the lattice, to destroy that lattice energy and move them back into the gaseous state infinitely far apart from each other. That's kind of our definition for lattice energy. Lattice energy depends on two things: the charges of the ions in question, and the larger the charge, the larger the ionization energy, divided by the distance between the ions. So really small, highly charged ions will have greater lattice energy. So what we're looking at here is we're looking at the charge on the cation and the charge on the anion. We have a constant, don't worry about that, but this is, let's say, the charge on the cation, this would be the charge on the anion, and the product of the charge of the cation times the charge on the anion divided by the distance. That's why when you have smaller atoms, and everything here has the same charge, they're all alkali metal cations, and we're using chloride ion as the only halogen here. So we've got the same anion in every case, but we're going down the periodic table from lithium to rubidium. Now, as you go down the periodic table from lithium to rubidium, the trend is that the element gets larger, even the cation gets larger. So lithium chloride bond, ionic bond, 257 picometers, and the rubidium chloride bond 333 picometers. Since the charges are all the same, you would have a higher lattice energy for lithium chloride because they're closer together. The positive and negative charges are closer together. Okay? So if you increase the radius, you reduce the lattice energy. So here's the lattice energy for lithium chloride, minus 834 kilojoules per mole, and here is the lattice energy for cesium chloride, which is minus 657 kilojoules per mole. Why is lithium chloride? Why does it have a higher lattice energy? Because the lithium cation is much smaller. You get those positive and negative charges closer together. Just think of magnets. If you get magnets closer together, the attraction is stronger. Same difference with cations and anions. So here we've got the same cation. It's sodium in every single case, but we've gone down the halogens from fluorine to iodide ion for sodium fluoride because sodium is smaller. Fluorine is smaller. You have a minus, it's all due to the fluoride ion being smaller. You have a minus 910 kilojoules. Sodium's a little bit larger, and so the lattice energy is becoming less negative, meaning it's weaker. It's not as high a lattice energy. And then minus 732, minus 682, because the iodide ion is so much larger than the fluoride ion. And so you have a much lower lattice energy. Remember, the more negative, the more energy that's being released. This is an exothermic experimental value. So lattice energies are going to be negative. Ionic bond lengths and lattice energies for lithium fluoride and magnesium oxide. So here's the deal. Look at lithium. Lithium has a +1 charge. Fluoride has a -1 charge. The bond length, 209 picometers, and you have a lattice energy, the amount of energy released when the lithium cation and the fluoride anion get together. They release 1,030 kilojoules per mole. So let's look at magnesium oxide. You have a +2 oxidation state or charge on magnesium. You have a -2 charge for oxygen. So you've got bigger charges, and the radius is still very close to the lithium fluoride radius at 212 picometers. But look at the lattice energy. Because those charges are so much bigger and the size is not that much difference, the bond length is very close to the bond length of lithium fluoride, you get a huge release of energy. So in this case, you'd have the constant for this, you'd have +2 times -2, which would give you a -4 divided by the 212 picometers between them, as opposed to lithium fluoride, which would be a +1 times a -1, which would give you -1 divided by 209 picometers. All right. So in looking at the way lattice energy is calculated, you're going to wind up with this. This is like one of the higher lattice energies for ionic compounds that you're going to find, the magnesium oxide. So you're looking for the big charges and the small radius. So let's take a look at this clicker question. Which compound is likely to have the most negative lattice energy? Remember, when we're talking about most negative lattice energy, we mean the highest lattice energy. Okay, highest lattice energy, meaning strongest attraction, hardest to break up. Okay, and that can affect things like solubility, melting points. Yeah, so we're looking for the highest. So here's sodium right here, and it's got a +1 charge as a cation. Okay, so there's a +1. Here's fluorine, and fluorine as an anion has a -1. So we got a +1 times a -1. Their fluorine is really tiny. It's smaller than anything else here. Sodium's a little bit larger. Here we've got magnesium fluoride. Now here's the deal. I've got a +2 charge here and a -1 charge here for the fluoride ion. So that gives us a bigger positive charge on magnesium. You've got a couple of fluoride ions. At -1, fluoride is really small. Magnesium is what? What's the trend for size? As you go from left to right, everything gets smaller. So magnesium, not only does it have a, a +2 charge to sodium's +1, it's also smaller. So given that, and then if we look at chlorine, chlorine's larger. Even though we have magnesium with a +2 charge, chlorine is down the periodic table. And as you go down the periodic table, everything gets larger. The atomic radius gets larger. So these two will be further apart than magnesium fluoride. So magnesium fluoride, that's our winner. Uh, in terms of charge, fluorine and chlorine have the same charge. Fluorine is smaller. Magnesium has a +2 charge, plus it's smaller than sodium. So this is actually the big winner right here. Okay, let's go ahead and arrange the following compounds. So here's what we want to do. I've got magnesium chloride. Magnesium has a +2 charge. And here are our chlorine atoms. There's two of them. I'm just looking at the charge here. And then let's see, we've got sodium +1, fluoride -1. Fluoride's pretty small. Cesium has a +1, and fluoride a -1. Cesium's huge. That might eliminate it. And then scandium, that's going to be a +3 because nitrogen is a -3. That's the nitride ion. So I'm going to automatically say that this is numero uno because these big charges. 3 times 3 is 6. That's a nice big -6. This is still a -1, -1, and this is a -2. So this is by far and away going to be the biggest. The next one, I'm going to look because of magnesium's +2 charge. It's also smaller than sodium. So right now, this is what I'm thinking. Scandium nitride has a higher lattice energy, higher melting point, harder to break apart than magnesium chloride, okay, which is going to be next on the list. And then sodium fluoride, because fluoride is so small and cesium is huge. So that's going to be NaF, and then I think cesium fluoride is going to be the loser there. So looks like this is the order of lattice energy from lowest to highest lattice energy. Okay, lattice energy, that's the amount of energy that is released. This is exothermic. The amount of energy that is released when gaseous cations and anions come together to form an ionic compound. Okay, that is chapter 9, ladies and gentlemen. I'll make sure to give you a nice exit ticket and activity covering Chapter 9. I'll give you plenty of time to do it. All right, that's it.